Hello and welcome to another stats warm-up. So let's see what we have here. The normal distribution with mean 6.8 and standard deviation 1.6 is a good description of the Iowa test of basic skills, basically a standardized test for 7th graders. Call the score of a randomly chosen student X for short. Find the probability that X is greater than or equal to 9. So again, this is a continuous random variable. And when we're dealing with continuous random variables, we're going to be using our NCDF. Now, what's good about this unit and going forward is we no longer have to turn this into a z-score. We can just say, all right, we want to do 9 and above when the mean is 6.8 and the standard deviation is 1.6. And we can let the calculator do the z-score conversion part for us. So second distribution, NCDF, lower is 9, upper is 9999, 6.8, 1.6. And we're going to get our answer there of 0.0846. So 0.0846. All right, but when we're dealing with a continuous random variable, we just are using NCDF the way we did way back in Unit 2. How many close friends do you have? An opinion poll asked the question of 1,100 adults. Suppose that the number of close friends people claim to have varies from person to person with a mean of 9 and a standard deviation of 2.5. So those are going to be two things we want to highlight. When the survey is conducted over and over again, the mean response varies according to a normal distribution with a mean of 9 and a standard deviation of 0.075. What is the probability that X is going to land between 8.9 and 9.1, i.e. the probability that the sample result estimates the true mean within plus or minus 0.1? All right, so the big question here is basically, which standard deviation are you using? All right, now, this standard deviation is for the individual. This is saying, hey, when we look at an individual, just one person, the standard deviation on their number of friends is 2.5, right? And since 95% of observations are within 2 standard deviations, we're basically saying, most people are going to have between like 14 and 4 close friends, right? 5 above and 5 below. This standard deviation over here is referring to the sample average, all right? So when we talk to 1,100 people, this is saying, okay, the average is still 9, just like it was for the individual. But when you're talking about 1,100 people, the standard deviation is going to be a lot smaller because those high people are going to be balanced out by the low people. And it would be really weird to talk to 1,100 people and be way up at 14. Because again, the highs are going to balance out the lows. So as our sample size increases, our standard deviation tends to go down because those kind of outliers are balancing each other out and kind of giving us, kind of counteracting that. So again, this is the mean for an individual person. This is a mean for all 1,100 people averaged together, all right? And this is going to be much more stable because it's over 1,100 people than just this, which is really talking about the individual. So since this says the probability of the sample result, we're going to be using these two values right here. All right, so it's going to be an NCDF 8.9 to 9.1 when the mean is 9 and the sample standard deviation is 0.075. All right, if this had asked, what are the odds that a given individual will have between 8.9 and 9.1 friends, then we would have used this. But since it's saying what's the probability that the sample result is between 8.9 and 9.1, we have to use the standard deviation for the sample. But then once you figure out which one it is, it's really just going in here, normal CDFing it, 8.9, 9.1, average of 9, standard deviation of 0.075. All right, and we get 0.8176. So again, if you take this sample over and over and over again, 82% of them are going to be between these two values. All right. So number 3 is now moving us over to the world of discrete. So both of these were sort of continuous, set up in this continuous fashion where we're working in means and standard deviations. Now we're going to go over to sort of the discrete situation where we have like a table of values and percentages. So the first question says, is this a legitimate probability model? How can you tell? All right. The way something's a legitimate probability model is if it covers all possibilities and those probabilities sum to 1. So if we take 3.01 plus 0.176 plus 0.125 plus 0.097 plus 0.079 plus 0.067 plus 0.058 plus 0.051 plus 0.046, they're going to sum to 1, which is exactly what we wanted. So yes, this is a valid probability model. So yes, this is legitimate. All the options are listed, and the probabilities sum to 1. Okay. So what is the probability that x is going to be greater than or equal to 6? So in this case, we don't have to use NCDF. We just get that information straight from our table. So we say, okay, there are the values that are greater than or equal to 6. So we're just going to sum those probabilities together. 0.067 plus 0.058 plus 0.051 plus 0.046. So 0.067 plus 0.058 plus 0.051 plus 0.046. And when you add those all together, you end up with 0.222. All right, so no fancy NCDF here, just taking those boxes, adding them together. All right, it's the difference between the discrete situations and the normal distribution or continuous situations that we had up here. Consider the events A, the first digit is 7 or greater, and B, the first digit is odd. What is the probability of A? What is the probability of B? All right, so probability of A is that the first digit is 7 or greater. So if we go back to our chart here, this would be 7 or greater. So we're just taking this 0.058, the 0.051, and the 0.046, and we're ending up with 0.155. All right, so probability of A equals 0.058 plus 0.051 plus 0.046, which equals 0.155. Right? Probability of B, that the first digit is odd, is just going and collecting all of the odd boxes. So 1, 3, 5, 7, and 9, and then just adding those together. So we've got 0.301 plus 0.125 plus 0.079 plus 0.058 plus 0.046. All right. before I use enter, I'm going to use this to write these down. So 0.046 plus 0.058 plus 0.079. And what were the other two? Plus 0.125 plus 0.301. And that equals 0.609. All right, so again, just using that chart, identifying which ones apply, and then summing those together. Next question is, what is the probability of A or B? Remember, that's the probability of A plus the probability of B minus the probability of A and B. So the probability of A we found was 0.155. The probability of B was 0.609. A and B is basically the ones that we double counted. So we double counted 7 and 9 here. All right, so those were double counted, 0.058 plus 0.046. There was basically 0.104 that got double counted. It got counted as part of event A, and it got counted as part of event B. So we would want to subtract out that 0.104. Now, because we had a table, you could have also just added up the ones and say, all right, adding this one, this one, this one, this one, this one, and this one. But since we had already calculated those two, we might as well use the general rule and just say, okay, we've got those two numbers. Now let's just subtract those numbers to arrive at our final answer. So 0.155 plus 0.609 minus 0.104 is 0.66. What is the expected value of the first digit in a report that follows Benford's law? Again, expected value is basically just another way of saying what is the weighted average. All right, and we can find that by doing probability times payoff, and we just add up all of those, all of the probabilities times all the payoffs. Now, we could do that by hand and do 1 times this, plus 2 times this, plus 3 times this, plus 4 times this, plus 5 times this. But I'm going to put it into the calculator instead. All right, so into L1, I'm putting my values. Into L2, I'm putting my probabilities. And then I'm going to run one var stats with a frequency list of L2. All right, so I've already gone in and typed all of those in. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are the values. And then those are the probabilities that go along with those values. So if I go to stat calc, one variable stats, L1 is my list, L2 is my frequency list, and then I calculate that. All right, it's going to give me the average value of 3.441. So 3.441 would be my expected value, which again is really just a weighted average. And then the reason I did it on the calculator is pretty much everything I did here is the same exact thing I have to do down here. So there's my standard deviation. Remember, we don't actually have a sample here. That's why this is blank. We're doing it off these probabilities. So all we have is the population value, and we can write that down as 2.4618. So 2.4618 would be our standard deviation. Now, what would the standard deviation and expected value be for a report where someone made the digits 1 through 9 equally likely? So let's just talk about this for a second because I didn't actually read this at the start. But Benford's law is this idea that when you're looking at like financial statements, the leading number follows a certain pattern. So basically, when you're looking at financial statements, more values start with 1 than start with 9. More values start with 2 than start with 8. So there's this distribution of what we expect numbers to start with. So basically, there's going to be more 1,000s than there's going to be 9,000s, or there's going to be more 100,000s than there's going to be 900,000s. Or if you're a big company, there's going to be more 1 millions, 2 millions, 3 millions than there are 7 millions, 8 millions, 9 millions. All right. So again, they tend to follow this pattern. And this pattern reveals that the weighted average is generally going to be 3.441, and the standard deviation is going to be 24618. All right. This is saying, what if there was no Benford's law? What if all the digits 1 through 9 were equally likely? So what I've done is I've gone to my stat edit, and in L3, I've given each one of those a probability of 1 divided by 9. All right. So if there's 9 numbers and they're equally likely, each one is 1 divided by 9. And if I rerun my one variable stats now, but instead use my frequency list as L3, all right, because that's where I put those equal probabilities, you're going to see that the expected value changes to 5, and the standard deviation changes to 2.58. So what do you notice about the two values from the fake report compared to the Benford's law report? How could we use this information to detect fraudulent reports? The standard deviations are fairly similar, but the expected value is much higher. All right, 3.4 all the way up to 5. So we can use this sort of as a measurement of, if I analyze, 1,000 financial transactions, and the expected or the average value of the first digit is closer to 5 than it is to 3.4, then I have reason to believe that somebody was faking those transactions and putting in numbers that they thought were accurate, when in fact they were just kind of like randomly picking them. And by randomly distributing them, they ended up with an expected value that was far away from this. All right, so how could we use this information to detect fraudulent reports? Calculate the average first digit in the reports, and compare it to what we would expect from Benford's law. All right, so again, just an example of how this sort of math and how this sort of thing can be used, out in the real world. This is like fraud detection. All right, so this is one way that this can be applied, and it's just one of many, but it does show you a place where this gets applied. All right, so again, both mostly, discrete, you're working off these charts and using the charts to answer the various questions, and then continuous, you're working with the normal distribution and using that to get the answers that you need. All right, hope this was helpful. As usual, if you have any questions, just let me know. All right.